Okay. We're going to get into now is we're going to think about geometry, right? We've got Lewis structures down. We got a good 2D picture. We're going to take this into 3 dimensions, and because remember the universe is 3 dimensional, um, and look at what do these molecules and stuff actually look like? What is their shape? What's their geometry? How does this stuff work? Okay. To do that, we're going to use VSEPR theory. Okay. Uh, there we go. Okay. VSEPR theory. VSEPR stands for valence shell electron pair repulsion. Okay. And that's just a fancy term and for saying that electrons want to be as far away from each other as possible. From each other. There we go. Okay. So what happens is all the electrons are trying to get as far away from each other as possible because having two negative charges close to each other stresses them out and that has high energy. In order for them to do that, they just kind of push away from each other. But they're all still tied to the central atom. So when they're tied to the central atom, they can only get so far away from each other. But then they're stuck because they're also tethered to that central atom. And that's what's uh, keeping us through all of this as we go. Okay. When we're thinking about shapes of stuff, we're going to use two terms and they get mixed up and confused. I have a system that I use to keep things straight. So let's think about this. We have a term called geometry. And I usually am very redundant with how I say things just so that we're clear about this. Geometry is about the electrons. Okay. How are those electrons arranged? Sometimes we say electronic geometry or electron geometry. How are the electrons arranged in 3D space? Okay. And you might think, okay, this is going to get odd, but really we're only talking about 5 ways that you can arrange your electrons in 3 dimensional space. There are others, but we're going to limit ourselves to 5. Um, the other term we use a lot is shape. Okay. Shape is the atom arrangement. Okay. Sometimes we refer to shape as molecular geometry. Okay. But that's awful. Electron geometry, molecular geometry, it's just too much use of the word geometry. So geometry is electron geometry, shape is molecular geometry, and we're going to try to keep things together along those lines. Additionally, so what we're going to, sorry, brain fart. Okay, slow down. What we're going to have to do is we're going to have to be able to count what we call electron groups. I call them electron groups, depending on what book we're using calls them different things, and I totally forget what this book calls them. But we're going to have to worry about electron groups. That's like goop. Electron groups. Okay, an electron group is just a set of electrons. This is set of electrons. It could be a lone pair. Those are obvious ones. It could be a bond. Okay, a single, a double, and a triple all count as one group. Okay, so when we're counting things, think of it as you're going to count how many lone, this is all on the central atom, and we're going to look at examples to do this as we go. But we're going to count things on the central atom, and we're going to count them as groups. So a lone pair counts as a group, a single bond is one group, a double bond is one group, and a triple bond is one group. Okay, so and if we're going to be counting groups, well, then we're going to have to know how this thing is put together. So this all hinges on having a good Lewis structure. Okay, that is key to getting this done. Okay, so what I'm going to do in this is we're going to walk through some videos. This VET interactive simulation that I've linked here, it's also linked in our course Blackboard, uh, is great. And I'll use this as well so we can look at things more three-dimensionally than just my crappy drawings. Okay. All right. So we're going to start off 2 electron groups. Okay. This is the lowest number we're going to have. 2 electron groups. Usually when we see this, this is 2 atoms connected. Here's an electron group. Here's an electron group. Same thing here. CO2. Here's an electron group. Here's an electron group. Right. If we're drawing out the Lewis structure for CO2, not like that. Brain. Okay. Notice we have lone pairs on the oxygens. Those do not matter at all. All we're doing is counting things on the central atom. And there's a double bond on each side. That's 2 electron groups. Okay. I love these doodles. These came from our book, I think, of balloons. And if we could do it, I would do it. But if you take balloons and you hold them in the center, they will kind of drift into the geometry that we're looking for. So if you hold 2 balloons at the center, they should be 180 degrees from each other. Anything that has 2 electron groups has a linear electronic geometry or a linear geometry, which means these guys are 180 degrees away from each other. That's as far away from each other as they can get. Ooh, excuse me. Okay. Um, all right. Let's look at that simulation. I'm going to spend a little bit of time switching between things. Where'd it go? It should be here somewhere. Okay. This is our course Blackboard. You can find this somewhere. This may change over time depending on how old this video gets. We're talking about VSEPR theory here. Here's our simulation. Okay, when you open this up, it's going to ask us if we want, there we go, if we want a model or if we want real molecules. It doesn't have every real molecule possible because that would be ridiculous. It would be awesome, but it'd be ridiculous. So we're going to go to a model. Anything that has 2 electron groups. Shoot, my thing's in the way. Okay. All right. It defaulted to give me something with 2 electron groups. You can change the number of electron groups over here by removing things or adding things as you wish. Okay. These are going to be generic and you can wiggle them around, but really 2 things is linear. You can see that's a straight line. We can show bond angles here like that so we can see them 180 degrees. If you like, we can do this. This is linear. This is linear. One thing to make a note of here is that if your bond order, if you don't have any lone pairs on your central atom, then your geometry and shape are the same thing. Okay. If you want to switch to real molecules in here, we can click real and then find somebody. CO2 is one we just did. Looks like that. Same idea. It's just giving you actual structure of stuff with the double bonds in there. Okay. Let me switch back to my slideshow. All right. This is 2 electron groups, 3 electron groups. Okay. Again, holding the balloons in the center, they're all going to kind of spin out along their own. And this is called trigonal planar. So what I want us to stress about in this is that the name of the geometry matches how many electron groups are there. So when you have 2 electron groups, your stuff is going to be linear. Okay. And if you have 3 electron groups, your electron geometry is going to be trigonal planar. Okay. If you have no lone pairs on the central atom, like this guy BF3, remember BF3, right? You can draw the Lewis structure however you want. The counting the electron groups in the center is going to tell us how many things are there and what the geometry is. But there's our BF3. 3 bonds, no lone pairs, that's 3 electron groups. It's trigonal planar geometry. It's also trigonal planar shape because there's no lone pairs. So remember, if there's no lone pairs at the center, then your geometry, I don't have enough room on here. Your geometry is equal to your shape. Okay, and they're called the same thing. So the geometry is trigonal planar and the shape is trigonal planar. Okay, if we give ourselves Like here's a good example of SO2. Look over here. Okay. If you look at SO2, SO2 is bent, and it's bent because we have this lone pair on the sulfur that's sticking out. And so we still have 3 electron groups, but it's because we have a double bond and a single bond and a lone pair. Okay. Let's grab our model and see what this looks like. Okay, I think SO2 is even in here. Yeah, SO2 is in here. Oh, and BF3. So there we go, BF3. Okay, trigonal planar. This looks nice. If you get it in the right way, you can see everything is kind of in the same plane as itself here. We can show our bond angles. All these bond angles are 120 degrees. Okay, and again, trigonal planar, trigonal planar. Okay, if we switch over to SO2, there we go. There's SO2. Notice we have that lone pair. Notice the exact angle on here is not 120. It says it's 119. I don't care. Okay. The lone pairs on there will tweak the angle a little bit. We're not going to stress about it. It's trigonal planar geometry, so the angles are 120. That's what it's supposed to be. All right, those are kind of the only 2 options we get here. You can be linear or you can be bent and 120 degrees. If we go back to our PowerPoint, right, you can notice over here that on the formaldehyde example here, right, it's given us the actual angles here. They're all close to 120, but they're not exactly 120, but they're close enough. This is trigonal planar. There's 3 electron groups. 1, 2, 3. Okay. That's enough for this one. We'll come back. We'll do other geometries in a minute. Okay. Let me know if you have questions. I'm here.